𝗂𝗽𝗱𝗁𝗂𝗁𝗂𝗁𝗂, who is research engineer at 𝗂�57 𝗂𝗍𝗂𝗃, and to present the welding quality detection use case that we've been working on in the research phase, the challenge that was built around it. So Welding, I leave you the floor.
Thank you, Nicolas. Hello, everyone. So for this part of today's talk, I will present how we designed an evaluation protocol for trustworthy AI through a real industrial use case. This work was developed in the context of an industrial challenge where the objective is not only to detect defects, but also evaluate models under realistic operating conditions, including robustness and uncertainty handling. So on one side, Renault Group provided the industrial use case, a welding quality inspection problem with real data, real constraints, and real operational expectations. On the other side, we have IRT Systemics. We were responsible for formalizing the problem from an AI evaluation perspective, designing and implementing the evaluation protocol, and coordinating the challenge. And this dual perspective is essential because it allows us to align industrial relevance with trustworthy AI principles and to evaluate models beyond raw performance. All datasets, evaluation protocols, and materials are publicly available, and if you want to have a look at them, you can visit the website of the challenge mentioned here. So the motivation behind this challenge is really straightforward. Trustworthy AI cannot be evaluated using one single metric. In real industrial settings, accuracy alone is misleading, and we must also account for robustness, uncertainty, handling, and operational constraints. Our first objective is to move from principle to practice. We build on the foundations proposed by 𝗂𝗽𝗱𝗁𝗂𝗁𝗂.ai program and translate them into a concrete operational evaluation framework grounded in real industrial constraints. Our second objective is to move from experts to communities. And this challenge is designed as a pedagogical reference, making trustworthy AI evaluation more understandable, reproducible, and actionable, beyond research settings. So here, if we have a focus within the W cycle to position our contribution. And in this work, we focus on the early stages of the cycle, starting with operational conditions, because this phase is critical as this is where the intended purpose is defined, the operation conditions and acceptable variability as well. And our goal here is not to optimize the models or their deployment settings, but to ensure that evaluation is grounded in real operational conditions. And this is where trustworthiness attributes can be meaningfully specified and where evaluation scenarios metrics are aligned with industrial constraints. And everything that follows in the challenge builds on this foundation. So here we focus on what drives the evaluation design. So we go from operational constraints, to evaluation applications. So we start from the operational context. It is an industrial visual inspection task integrated into production with strong safety and productivity constraints. These constraints translate into specific data characteristics, large-scale data, strong class imbalance, and high visual heterogeneity. And as a result, we observe critical issues that are non-uniform criticality across SIM types, a significant fraction of low visibility samples, and naturally occurring out-of-distribution conditions. All of this has direct implications for evaluation, and accuracy alone is misleading. We need scenario-based and conditional evaluation explicitly assessing robustness, out-of-distribution behavior, and uncertainty to reflect real operational risks. So here, some figures to illustrate a little bit of data constraints. So we zoom in the data-driven constraints that shaped our evaluation choices. So we see here on the left how we analyze the structure of data using clustering to reveal latent visual patterns across welding seams. And this helps identify groups of samples that are visually similar but operationally distinct. And on the right side of the slide, we complement this with conditional statistics focusing on blur distribution. And this analysis shows that data quality is not uniformly distributed. Certain seam types are systematically associated with higher degradation level. And here we focus on blur degradation. So the key message is that data constraints are structured and contextual and not random. And as a result, evaluation cannot rely on global averages. It must explicitly account for conditional effects, data heterogeneity, and uneven difficulty across operating conditions. So, all the previous observations directly lead to the selection of trust attributes, starting from operational constraints. So starting from operational constraints, which are safety requirements, production costs, and decision risk, we design an evaluation logic that is scenario-driven rather than metric-driven. We associate dedicated datasets, which are real data, synthetic data, and curated failure cases with specific trust attributes. Performance is evaluated under nominal conditions, robustness under controlled degradations and out-of-distribution scenarios, and uncertainty through the system's ability to express confidence or abstain from giving a decision. The outcome is a set of calibrated and comparable KPIs, one per trust attribute rather than a single opaque score. And this ensures that evaluation results remain interpretable, actionable, and aligned with industrial decision-making. Move to the next slide. So this structured mapping from data constraint to trust attributes enables a rigorous and operational evaluation protocol, which I will next detail. So at this stage, we move from operational constraints to evaluation design. Trustworthiness is treated as a multidimensional property driven by operational risks, data characteristics, and industrial constraints. From these drivers, we select trust attributes: performance under nominal conditions, robustness under degradation, and uncertainty handling through confidence and abstention. A key principle here is that a good performance does not imply robustness or reliable uncertainty handling. The evaluation protocol, therefore, is designed as a trade-off between completeness and feasibility to remain realistic in an industrial challenge. Once trust attributes are defined, the next question is how to make them actionable at the solution level. And at this stage of the W cycle, we focus shifts to solution API contract design, because evaluation requirements are translated into explicit interface level contracts, what the model must output, under which conditions, and with which guarantees. This includes predictions, uncertainty signals, confidence scores, and behavior under degraded or out of distribution inputs. By formalizing these expectations early in the cycle, trustworthiness is embedded directly into the system architecture rather than added post hoc. Evaluation results thus become design contracts that guide implementation, integration, and validation. We then move to the concrete specification of the AI component. The component receives images as an input and exposes a structured output contract. First, it produces decision output, OK images, OK welds that are good, KO for faulty welds, and a known, which translates that the system abstains from giving a decision. And this state is critical as it allows the system to tell us that it doesn't want to make a decision because the risk of error is very high. Optionally, the component outputs class probabilities, providing confidence information. And finally, an out-of-distribution score indicates whether the input lies inside or outside the operational data distribution. And each output is directly linked to trust attributes. Decision quality supports performance and robustness evaluation. Confidence outputs support uncertainty evaluation, and the OOD score enables irrelevance detection, OOD monitoring, and drift analysis. Trustworthiness is thus encoded directly into the component interface, making it observable and enforceable through the system lifecycle. So here, once the AI component is specified, we move to evaluation protocol and scenario design, and evaluation becomes tightly coupled to both the component specification and the operational context. So the goal here is to translate trust attributes into explicit evaluation scenarios. So this table shows how we designed our KPIs. Once the scenarios are defined, we construct metrics and KPIs. The key idea is to move from raw metrics to interpretable decision-oriented KPIs. So performance, for example, relies on classical metrics such as confusion matrix. Uncertainty focus on calibration, quality, and confidence reliability. Robustness is evaluated using controlled perturbations across multiple degradation levels. And OOD monitoring and data drift use dedicated data sets and detection-oriented metrics such as the rock group. Each attribute is summarized into an attribute-level KPI through aggregation and penalization aligned with operational risk. And these KPIs are then rescaled and aggregated into a global score, preserving interpretability and traceability. Once the protocol, scenarios, metrics, and KPIs are defined, the final step is evaluation implementation. And evaluation becomes an executable process embedded in the engineering lifecycle. So this slide presents the operationalization, of the protocol around 3 pillars: baselines, dataset families, and execution pipeline. So we design multiple baselines, functional baselines to validate the pipeline, artificial baselines for metric calibration, and realistic baselines with and without trust mechanisms. They serve as reference points to interpret scores and validate metric sensitivity. So evaluation datasets are structured into families aligned with trust attributes: nominal conditions, robustness perturbations, OOD monitoring, data drift sequences, and generalization datasets. All evaluations are executed through a standardized pipeline. Metrics are computed via common API, aggregated into KPIs, and combined into global trust score, ensuring reproducibility and comparability. Now this slide focuses on dataset production and pipeline calibration. The objective is to ensure that evaluation results are meaningful, stable, and interpretable. We start from scenario specification, defining acceptable operational variability. Sorry, I was reading messages, and ensuring representativeness across scene types and visual heterogeneity. Dataset production combines real data selection using clustering, anomaly scores, and labels with synthetic OOD generation using controlled perturbation. All datasets are manually qualified and statistically validated. Calibration is applied as a transversal layer across the pipeline. It includes baseline validation, metric sensitivity, analysis, and calibration of thresholds and aggregated weights. So this ensures a consistent transition from specification to evidence and from evidence to calibrated metrics. So the final step is pipeline execution and KPI reporting. At this stage, all design choices are fixed. We cannot change them. Models are evaluated through standardized execution pipeline. Metrics are computed automatically, aggregated into KPIs, and reported as structured, decision-oriented evidence rather than leaderboard scores. So this slide illustrates the validation and scoring lock-in phase. Controlled performance systems, ideal, degraded, random, and failure-oriented baselines are used to validate metric behavior. Each trust attribute is evaluated independently and aggregated into attribute-level KPIs. Once validated, the scoring logic is frozen, ensuring stability, fairness, and comparability across solutions. So here, this figure illustrates the validation, and it shows, sorry, I think someone moved my slides, sorry. So this figure shows how the participants' scores evolved over time. Early scores are very low, as you can see, reflecting optimization of nominal performance only. At first, plateau appears around 30-40, corresponding to models that perform well nominally but fail on robustness or uncertainty. And the major jump occurs when participants explicitly address multiple trust attributes jointly. Scores above 80 are only reachable when robustness, uncertainty, and OOD handling are all addressed. And this progression validates the evaluation protocol itself. It rewards meaningful improvements, not metric overfitting. So for the takeaways to conclude this work, trustworthy AI evaluation must be engineered, not assumed. It requires explicit design choices made early, what we evaluate, under which conditions, and why. Multi-criteria evaluation is essential in safety-critical systems. Operational constraints and failure modes must drive evaluation design from dataset construction to metric aggregation. Next, synthetic stress tests are curated real-world failures and complementary. And finally, iterative validation is what makes leaderboards credible and abuse-resistant. Overall, this challenge illustrated how evaluation protocol can actively steer innovation toward trustworthy AI system. So thank you for paying attention. I think we have time for questions. So do not hesitate if you have any.
So do we have question on the chat? I don't know if you could see any question related to the challenge.
Yeah, I think we already answered for one about I think the library and how to evaluate and train and to do the experimentation. And the last one we get right now, I didn't. Yeah, I will. Yeah, it's around the ODD. I don't know if we can answer here. are you seeing the?
Yeah, so the question is about inferring ODD from the data you have instead of modeling the variety of operational conditions where your system is supposed to operate. I don't know if anybody wants to comment on that.
I don't know. Yeah.
Yeah, maybe I think we should maybe you should ask to the expert to respond on that. I'm not sure it makes sense to answer online. Maybe Kevin, if you have time.
Mm-hmm. And we have another question about.
No, let's move on. Let's move on. We will answer offline because I think we need to have some comment from the expert that just work on the ODD part. Maybe Carla, if you have a comment on it.
Yeah, I mean, real quick, maybe. So it is precisely the question just disappeared. So the question, if you can put it up again, I think it would be useful, 𝘂𝘁𝗂𝘂𝗂. But it was regarding the ODD. How do we define the ODD, and can we just define it based on the data that we have? It is precisely the type of approach that we're trying to avoid, because in this sense, we are really just depending on the model/components that we can have, the data that we can have, and based on that, we can deduce what kind of system we can build. We're trying to approach the challenge the other way around. So we have a system. Do we have a why for integrating AI into the system? And if we do, then we need to know what the system is supposed to do in its environment, in society, wherever it is supposed to, in industry, whatever it is supposed to evolve. Based on what we want to provide as a service, then how do we derive, how do we specify, how do we formalize what we need to ensure? And then can we see what we have as available in data? And there's something that maybe has not been said. There's going to be iteration in that sense. Maybe we define an ODD and we don't have the available training data. That can be true. And in this sense, the entire cycle that was very well illustrated by William provides the means to just go back, adapt the ODD, but you need to then adapt potentially the intended purpose. Then you're going to be able to limit your ODD, just not base yourself in the training data and just deduce a system based on that. That would be my quick answer, and I'm not the specialist in this, but it will be my quick answer to that.
Okay, thank you, Carla. I think that we have still some time to answer to other questions. Of course, I think Kevin also, you can join us because he worked a lot about this challenge. So how the global trustworthiness score calculated as attribute specific metric typically have different semantic range units, etc.
So I don't know if Kevin is here. I'm trying to go back to the slide where can you put the question up again, please? 𝘂𝘁𝗂𝘂𝘂?
Yeah, but I can put it only one time.
Okay.
I don't know who stopped it.
The question is, how can we combine the different scores to build one aggregate score?
I will do it again like this.
Okay. So Kevin is the one who did the work, but obviously he's not with us at the moment.
Maybe if you want, I can answer in generic way. I think there's definitely the aggregation of component to identify one score is something that is very difficult because you have a lot of dependency between the components. You cannot say that we can apply a basic linear combination of those things. So what has been done, and maybe some of our researcher could tell more about that, but we started to build a mix between a linear combination, but also some additional ways to make sure that the output of this linear combination will not be completely out of a scope based on the industrial requirements. So sometimes we define some level and some trigger, non-linear trigger that have been applied on this. So it's a combination of both. And you explained that this has been evaluated through also the data set, so that we calibrate. This is what you call in terms of calibration phase. We make sure that the linear combination, but also the trigger we have defined in this case will be relevant with the current use case we have done. So basically what I'm saying, it's not so easy to mix and to aggregate combination. What we have done here is a set of linear combination plus some additional, let's say, trick in order to make sure that we can provide something that is accurate for this use case we are working. But there are a lot of research topic on this area, and I'm quite sure that we cannot say we have a complete answer to provide an aggregated score for any kind of use case, any kind of problem today. And of course, if maybe we'll have a complete and maybe a more research-oriented answer, maybe offline after this meeting.
I just want to add a quick thing. So the aggregation was based on the impact of each attribute on the evaluation. And if you want to have more answers or more insight about this, I invite you to visit the website that I mentioned earlier. And we detailed how we did the calculus. So I think you can have your answer on the website.
Okay, thank you, Jan and Wian. So I can add another question, maybe. Yeah, two questions from Laurent Desmet. So I start by this one. And which uncertainty quantification algorithm did you use, and how do you calibrate it? Maybe if you have some information about it.
Definitely, I think it's something that our experts should be able to answer to this, but I'm not sure they are online and we have time on that. But definitely, I would, if you have some specific question on this, let's try to answer it offline, and maybe you can reach out to. We make sure that we make the connection with all the researcher that has been working on that. But I'm not sure we have time and the people online to answer.
Yeah, I think in the same time we have a deep dive in the second part. We will talk about uncertainty quantification. I think that we can answer and give more detail about this question.
Yeah, and yeah, Kevin will answer offline, maybe on the chat later on. He told me that he just tried to answer to write an answer on this topic later on.
Okay.
Maybe a general comment on that.
Yes.
What I would like to highlight to all our audience is that here it was a concrete example of how the methodology and tool are used to deliver a multi-criteria evaluation pipeline that meets with real industrial use case expectation. And this, what we have seen also with the methodology is that this could be applied during the engineering phase, because you saw that we were able to improve the model based on the ability for the engineer to use the engineering pipeline or multi-criteria evaluation pipeline, but also that could be used also during the evaluation by EVVQ teams. So these kind of things could be relevant definitely at the engineering phase, but also at the evaluation phase. And what I would like to do also is, from the association perspective, we are very interesting to try to do the same kind of work with additional use case and with additional industrials. So I just make a kind of call for new challenges. If you are interested as an industrial, or if you have some use case you would like to promote, and you would like us to help you in using the end-to-end methodology to reuse this kind of exercise, again, please let us know. And I think this is definitely something we want to do this year.
Okay, thank you, Jan. I think we have a last question. It's about the robustness. Of course, if we implement the robustness by adding some noise and
Okay, looks like we lost
something weird happened. Could you please come back to stage? Yes, thank you, 𝘂𝘁𝘂𝘁𝗂𝘂𝘁.
𝘂𝘁𝘂𝘂𝘁, I think you are still not on stage.
now
You're back.
okay, thank you.
Welcome back, 𝘂𝘁𝘂𝘂𝘁.
Thank you.
Last question.
So yeah, for the business, yes, there is a stability of the model evaluation, and of course we added some noises in the pictures, and we of course we evaluate our business on this way also for the challenge. This is what just I want to say that yes, of course we did this kind of evaluation of our business.